So we've come across the ratio test before because this is a way for us to find our preliminary interval of convergence. Please note it is a test for absolute convergence, so I need non-negative terms. The way we get around that is, if you notice in my limits here, I put everything in an absolute value. It forces everything to be non-negative, which is awesome. That works great for us that way. And this is kind of our trick anytime we're doing a test for absolute convergence, is we just stick everything inside an absolute value. And we talked about how when we were finding our preliminary interval of convergence, when we do the ratio test, the series converges if the limit of the comparison of the n plus first term to the nth term is less than 1. Diverges if the limit of the comparison of the n plus first term to the nth term is greater than 1, and is inconclusive if that limit is equal to 1. In other words, we would have to use a different test. And this is why it's useful for preliminary. At the endpoints of the interval of convergence, the ratio test would, when we do that limit, would equal 1 and is inconclusive. That's why I just call it a preliminary interval of convergence. This is a wonderful, wonderful test if you have exponentials and factorials, because the canceling when you're comparing the n plus first term to the nth term is really nice. It can be hard to use on a rational function. So some examples here. If I have the series where n goes from 1 to infinity of n times 1/2 to the n over 10 to the n, that's one where it doesn't seem super easy to me to try the nth term test. It's not a geometric series because I have 10 to the n and n both outside of the 1/2 to the n, so it's not geometric. It's not a p series. So I'm trying ratio test then. So that means I'm doing the limit as n goes to infinity of the absolute value to make sure everything's non-negative of the n plus first term compared to the nth term. So that gives me the limit as n goes to infinity of the absolute value. I have n plus 1. 1/2 to the n plus 1 is the same as 1/2 to the n times 1/2 to the first. 10 to the n plus 1 is the same as 10 to the n times 10 to the first. And then I'm dividing by fractions, so it's the same as multiplying by a reciprocal. And I can see then that a 10 to the n will cancel, 1/2 to the n will cancel. And I've now got the limit as n goes to infinity. It's good to gather our n's in one fraction inside anything that's not an n in a different fraction. So I have an n plus 1 over n times 1/2 over 10. The reason I like to do this is, according to the limit, n is the only thing that's changing. Anything that's not an n is a constant and can be pulled out of my limit. So I have the absolute value of 1/2 over 10 times the limit as n goes to infinity of n plus 1 over n. I can use an n behavior model because n is going to infinity, or I could do L'Hopital's rule because n plus 1 is going towards infinity and n is going to infinity. Either way, if I do n behavior models, this is n over n, which is 1. I get that this limit is going to equal 1/20th, or the absolute value of it, which is still 1/20th. Well, that is less than 1, so this must converge by the ratio test. If I look at my second example, I have the series from n equals 1 to infinity of n factorial times 1/2 to the n. I could do the nth term test on this because n factorial times 1/2 to the n is not going to be 0. but it's not immediately obvious that that's true because the 1/2 to the n is getting smaller while n to the factorial is getting bigger. It's not a geometric series because of the n factorial. It's not a p series, so I'm trying ratio test. So I'm doing the limit as n goes to infinity of the absolute value to make this all non-negative of the n plus first term compared to the nth term. So the n plus 1 factorial is the same as n plus 1 times n factorial. 1/2 to the n plus 1 is the same as 1/2 to the n times 1/2 to the first. I can now see n factorial will cancel, 1/2 to the n will cancel, and I'm left with the limit as n goes to infinity of the absolute value of n plus 1 times 1/2. And since n is going to infinity, this is going to infinity, which is bigger than 1, so this diverges by the ratio test.